continue now, I hope. Well, let me declare open for the defense of thesis, Sedov Maksim for the degree of candidate of physical and mathematical sciences, specialization 010421, laser physics, on the theme simulation of characteristics X-ray radiation from a femtosecond laser plasma. Declare open. I didn't ask you for permission to stay seated. According to the orders in Petersburg University, dated November 12, 2019, me, Timofeyev Nikolai Alexandrovich, Doctor of Physics and Mathematics Professor, Head of the Optics Department at St. Petersburg University, was appointed Chairman of this Dissertation Council. Now let me introduce my colleagues, Council members who will have taken part in today's meeting. On my right, of Mashik, Igor Chislavich, Doctor of Physics and Mathematics, Associate Professor, Department of General Physics, St. Petersburg University, and also Head of the General Physics Department. And in remote mode, we have 4 colleagues today. It's a first experience like that for me. So many remote participants. Hopefully that will not interrupt us. Let me introduce you. Savelyev Trofimov Andrei Borisovich, Doctor of Physics and Mathematics Professor of the International Laser Training and Research Center of Lomonosov Moscow State University. Sergeyev Vladimirovich, Doctor of Physics and Mathematics Professor of the High Engineering Physics School of Peter the Great Polytechnic University, St. Petersburg. Bychenkov Valery Yurovich, Doctor of Physical and Mathematical Sciences, Senior Researcher, Acting Head of the High Energy Laser and Plasma Physics Sector of Institute of Lebedev Physical Institute of Russian Academy of Sciences, and Oks Yevgeny Alexandrovich, Doctor of Physical and Mathematical Sciences, University of Auburn, USA. According to the federal law on science and the scientific and technical policy, our university, by corresponding order, is awarded the right to award academic degrees independently. The order was issued on the 1st of September 2016. In accordance with this order, a session of the Dissertation Council is duly constituted if at least 2/3 of the approved members of the Council are participating, but not less than 4 persons. Our Council consists of 6 members. All the members are present, including 4 members in the remote interactive mode. The audio-visual contact has been established with them. Thus, there is a quorum, and we have the right to start. Let me introduce the procedure of today's session, which hopefully will not take more than 2 hours. First item, the Chairman's summary report on the main content of documents submitted by the candidate and their compliance with the applicable regulations. Answers to possible questions, 5 minutes. Second, brief presentation by the applicant outlining the key points of his study. It says 15 minutes, but traditionally a candidate's thesis traditionally takes about approximately 20 minutes. So if you can stay within time limit, be nice. Questions to the applicant strictly on his report and answers of the applicant. 4, speeches of all members of the Dissertation Council in turn with their reviews, with stating their opinions, questions and suggestions to the applicant. 5, speech of the Chairman in his review. 6, answers of the applicant to questions and remarks members of the Dissertation Council. 7, open discussion, speeches of all attendees, and at that, I'm kindly requesting all the attendees to put their names on the registration sheet and introduce themselves before speaking. 8, final answers of the applicant to any questions asked. 9, speech of the academic advisor, Alexander Alexeyevich Andreev. 10, a 5-minute discussion before the open voting on awarding or not awarding the academic degree to the candidate. For that time, broadcasting shall be suspended. 11, open individual voting. The Chairman of the Dissertation Council shall count the votes and results shall be recorded in the minutes of the meeting. 12. Decision on awarding or not awarding the academic degree of St. Petersburg University to the applicant, and closing remarks of the applicant. Before we start this procedure, but lengthy, let me remind you to switch off your mobile phones. Thank you for your understanding. Let me also inform you that our meeting should be translated and recorded from Russian to English or from English to Russian. Well, since all our colleagues can speak Russian, I don't think anyone needs translation here. Otherwise, but I think the English translation shall be broadcast online. Well, item 1 of our agenda, Chairman's Summary Report. The thesis by Sedov Maksim Vladimirovich for the degree of Candidate of Physical and Mathematical Sciences, Specialization 010421 Laser Physics, on the theme Simulation of Characteristics X-ray Radiation from a femtosecond Laser Plasma, was accepted for defense by the order of the Academic Secretary of St. Petersburg University, dated 11th November 2019. The Dissertation Council was appointed by the order of the Academic Secretary of St. Petersburg on the 12th of November 2019, and I have already introduced its members, and I am, as already mentioned, I am the chairman of the council. The applicant submitted the following documents to the academic secretary of the university. Application to the rector of St. Petersburg University, Professor Kropocher, to accept the dissertation for consideration and defense, submitted on the 17th of September 2019. A review from Andreev Alexander Alexeyevich, Doctor of Physics and Mathematics, Professor of the Department of General Physics of St. Petersburg University. A list of 5 publications which set out the main scientific results of the thesis, including in peer-reviewed scientific journals from list approved by the Ministry of Education and Science of the Russian Federation, 3 publications. In publications indexed in the scientometric databases Web of Sciences Corpus, 2 publications. Certificate of candidates examinations issued. Sedov Maksim Vladimirovich passed the candidate exams in specialty 010421 Laser Physics for the mark excellent, history and philosophy of science, physics and mathematics excellent, and English also with an excellent mark. A diploma or master's degree issued on the 17th of July 2012 by St. Petersburg University, certifying that Sedov Maksim Vladimirovich was awarded the qualification of Master of Physics, and conclusion of organization, on the basis of which the thesis has been produced in St. Petersburg University. 7. The thesis in Russian and in English on paper, on the rise of manuscript, and in the electronic form. The thesis has been formatted in accordance with the requirements of the State Standard 7.0. I'd like to say that all the documents listed above comply with Clause 12, Section 3, thesis presentation and defense. The procedure for awarding academic degrees at Petersburg University. Does anyone have any questions to me or to the applicant? If no one has any questions, let me give the floor to the applicant, Sedov Maksim Vladimirovich. Please, let's make it 20. Please make it 20 minutes. Thank you. I will try. As you know, the theme of my thesis, and it can be. I'd like to divide into 3 parts. Second part, radiation of helium lines, and in conclusion I'd like to tell you how this modeling algorithm can be applied for theoretical optimization and parameters of laser plasma X-ray source. Let me start with some introduction. One of the most significant achievements of modern optics is introduction in the experimental practice of complex sources of laser impulses. To date, the maximum achievable intensity is interaction with matter. A plasma with unique characteristics is formed on the target source with unique characteristics. It's called femtosecond laser plasma. There are several known mechanisms in such plasma. There are several mechanisms such as radiation from hot electrons, generation of high charged ions, and thirdly, as laser radiation is reflected as in X-ray range, and various recovery processes, etc. In my paper, I mainly engage in the study of radiation and, to less extent, recombination radiation. Let's take mechanisms of generating such radiation, how they differ from each other. Hot electrons, directly accelerated by the laser field, fly deep into the target and counter neutral color, which will knock out an electron from lower. These vacancies are filled, and an alpha photon is released. It should be noted that vacancy can be filled with an electron with a higher shell, for example. In this case, better fill. So what's the difference? These lines these differ, but ions on surface plasma, they can get into irritated state. Same transition, but because of naked ions, so the energy is shifted. So here we may see in this an example of this. This spectrum is different from laser plasma. So here again, all the lines can be seen very clearly here. Complete description of the interaction of short laser pulses with are quite complicated and have not been conducted. Complete model shows and so the methods of numerical modeling are effective. For modeling, we use so-called an algorithm is an electron divided by energy, and then how Monte Carlo method automation is developed by Klimo, suggest taking account the influence of laser pre-pulse using hydrodynamic simulation, but its full integration with calculation has not been made. In my work, a hybrid simulation algorithm which can be used as alpha from square centimeter. So that's how it this picture shows how it works. Initial parameters of laser emission and the target intensity, duration, and angle of incidence of the laser parameters before the pulse, material, and thickness of the target. Then the control script written in the MATLAB language reads the input data, forms an input file. At the end of the reads the prof, and the main laser pulse arrives at the target, transfers it to calculation and starts calculation. This calculation starts as a second part of the script. Gets started by the time the Monte Carlo method, and have result. So what's the difference between this modeling from previous works? With integration of laser pulse with the target is possible. Secondly, it can be calculated yield from it can be calculated of electrostatic barrier. So new sort of ions has been identified, and a Monte Carlo calculation. Then see electron reflection from electrostatic barrier. For this hybrid modeling, see energy distribution. This distribution can be it emerged a long time ago. Alpha emission, etc. Yet most of these models look at hot electrons only. For example, here we may see 10-19 degree is and cold with 10 keV. And of course the energy, the distribution is so the distribution, this 10 keV will give. So we create our model, and the main principle here is laser magnetic field. And on the basis of this principle, the balance, and in the end we will get this formula that you can see at the top of the slide, because our efficiency, some hot electrons reach the barrier, get reflected, and weaken the flow. As a result, we get two equations. You can see and to make the system complete, we need two more equations for Wilks formula, because it includes self-absorption coefficient, and this. So we couldn't write this the formula ourselves for laser intensity. So we suggest to use, which is half empirical expression that you can see in the bottom of this slide. Density on laser intensity. So we get four equations, and can be included in the modified Wilks formula. Next slide shows comparison of distribution. We may see a hot parts coincide quite well. The cold parts coincide not so well. But important property of this model is that with its help, it's possible to describe influence of nanostructures on the target surface. The influence of nanostructures has been studied before. So we composed the following half empirical formula, and we know how absorption coefficient changes, because the temperature of hot electrons also changes immediately, and this affects counterflow and the temperature of cold electrons. And here we may see in this slide comparison with a distribution function 10 in the 20th, and on the right, hot electrons, as you can see, coincide quite well. Cold electrons, satisfactory coincidence. For calibration, analytical model, we conducted some experiments, a series of tests in St. Petersburg. The scheme is shown in this slide. I don't have the time to talk about them in details. So I will proceed to go straight to results. Relation with the conversion center on the angle with the help of this. So first we could calculate it in Medusa, scale lambda or higher, and then with the help of comparison with the analytical formula shown here, we figured out, use this coefficient of our further calculations. This slide shows the comparison of our experiments to model calculations. These curves, red dots show experimental results, black squares the calculations, and dotted line, a gray line, there's a model. And on the average, they more or less coincide. The curves more or less coincide. You see half black squares. These are our experiments, and half-filled squares. These experiments we conducted Zhavarenkov 9 years before. So the calculations coincide quite well with test measurements. Then we modeled the lines. So unfortunately, I don't have the time to talk about it in detail. The calculation was in 2 stages with help of hydrodynamics, density and temperature distribution. In addition to all this, we created an analytical model based on previous work of Andreev. As I understand, I don't have the time to talk about it also. So just show you the conclusion picture. And when choosing this concept, it corresponds quite well with the calculation, coincides quite well with the calculations. What makes this model good? It two-stage modeling makes the calculation process easier. Now I'd like to talk about parameter optimization for laser plasma, source of radiation. Maximum conversion is important, and shortening the impulse time, making the impulse time shorter. It's important. For conversion coefficient optimization, everything is clear. Since 30 years, scientists have been working, and so what they succeeded to achieve is shown in this slide. This slide shows calculations of conversion coefficient for aluminum, but the most interesting point here is that black squares and black line show calculation for foil. But we can see if we neglect absorption, conversion coefficient, so nothing can be added here. What's more interesting is how conversion coefficient is optimized. On the left, you may see the relation to the silver target. On the right, conversion coefficient for same target thickness. We use silver target, but 1 micron thick. Electrons get reflected and spend too much energy, so conversion efficient is lower. So which is novelty. And before, so that was something new we found. And also I'd like to say a couple of words on brightness. On the left you can see time output of silver foil, 10 in the 8th, gray line here. This Monte Carlo calculation, black line, Monte Carlo peak for 5 micron foil, and red line, that's calculation for peak calculation for 5 micron foil. So you can see the dependence here. They yield similar results, which means that modeling was correct. Also, you may see that peak intensity for endless target is higher than for foil. Time of impulse, full width by full height. For endless foil, it's smaller. And on the at the top, you can see valuations for brightness. Endless target, you get 20% brighter from foil, because we get no redirection. So brightness can be increased, still increased. If we use foil with the base, on the right you may see the calculations time for relation for silver target, different targets of different thickness. And so the brightest was electron 5 micron foil. Its brightness was 2 times higher of same type of foil with redirection or reflection. In case of 2 micron foil, with peak brightness is not much lower, but time 15 second was 50 milliseconds, which is too small, too short. And in this slide, you see the relation of brightness of silver and aluminum to laser intensity. You can see it's growing steadily, depending on laser intensity. And the red line is 2 times brighter than that of silver target. And here, this slide shows comparison brightness of such laser sources compared to all different photons, different generations and X-ray lasers, and you may see that is synchrotron radiation, the level of synchrotron radiation. With that, I would like to finish my presentation. Thank you, Maksim Vladimirovich. Questions, please? Dear colleagues, in remote mode, maybe you have questions to Maksim Vladimirovich? Let me slide 10. You show us a calculation. Is this the right slide? No, slide number 10. Please go to slide number 10. Distribution function. It's 10 in the 19th degree. This slide. Yes. Here, electron energy. 10 in the 19th. Maximum electron energy is much lower. And then several slides later, like 4 slides later, you get different result. You get a different result. Can you explain the difference? Electron energy. I suspect in this slide it's a misprint, so it's 10 in the 18th degree. So this must be my mistake, a misprint. More questions, please? I have a question. You developed a hybrid algorithm. Can be applied up to 10 in the 20th degree, but modern achievements is 10 in the 23rd degree, as you mentioned. So what do you need to make the application range of your instrument wider? From single dimension to double dimension calculations, such as laser field pressure, which can, secondly, nuclear reactions will start, which we should take into account. But the most is 2-dimensional calculation. Do you know if anyone has done that already? I haven't heard about this yet. I know that work is in progress. But for adequate modeling, 10 in the 23rd degree, I don't think you can get adequate calculations at this point. Igor Vyacheslavic, you had a question. In your presentation, you said a lot that you have no time to talk, but traditionally, So what can you summarize the provisions set forth for defense? I did. Yes, I did not. You have them. What are the most important points? So, what do you think is knowledge that what is new knowledge that you obtained? Unfortunately, I don't have a slide. But you have them in your thesis. But also, it makes sense to show them in your presentation. If I read them, it will take 5 minutes out of the 15 minutes I had. More questions, please? I would like to ask a question, please. Slide 10. These chosen temperatures, to me, for low, those the calculations and the temperatures do not correspond to each other. So it should be much lower. Did you measure the temperature by for model? It doesn't make any sense. This slide is the top border of the distribution function IC. More questions? Maybe any of the attendees? If no one has more questions, so next item. External reviews. We don't have, I understand, as I understand, we don't have any external reviews. So let us hear the reviews of the members of the Dissertation Council. Let's follow order let's follow the procedure. Thank you. I don't know what's the common practice in. Okay, this thesis is quite significant and relevant. Sources can be used, can have many applications, and calculation optimization is very significant. And in reality, what the applicant has managed to achieve is bringing together different codes, separate codes, peak modeling, Monte Carlo modeling, summarizing, put together into a system, and development of analytical models, which can be used, which make such calculation much easier. So in that sense, the thesis is interesting and significant. It's obvious. And here we have no questions of that. Maybe using my review, I'd like to focus more on some critical comments, significant critical comments. If I followed my review, there's a question about provisions set forth for defense. Unfortunately, we didn't see them. You should put them on a slide. And these provisions are reliable, and that's beyond any doubt. But the wording itself is unusual. It's not a statement. It says so it's like a description, not a statement, which is the common practice. And secondly, unfortunately, we we cannot have a picture. It's provision 2 is not, novelty is not obvious. As other authors tried to use different packages, probability. So they have done this earlier. So I think that provisions do not not well formulated. And then I have some comments to the contents, to the content. First comment: the author focuses too much on resonance absorption, but neglects anything outside this. The brake mechanism evaluation, neglecting this mechanism because it creates a background which affects all other processes. So removing this is incorrect. And second point connected to the same is such concentration gradients described of laser radiation. A significant role can be played by agitation and disintegration concentration. And again, you don't mention these processes. So that was the first point, my first point. You focus too much on resonance absorption. And the second comment, which I included in my review, before impulse, firstly, using single dimension hydrodynamic, I think is bad for this, because it works for short times only, and then with a growth of plasma flow it becomes much more complicated and cannot provide accurate description, not to mention plasma instability or possible turbulent flows. Even this plasma torch single dynamics is hard to describe. Yet when the author describes where plasma comes from, there's some short impulse which generates it. Yet for spontaneous luminescence, the author doesn't say anything. This radiation, because it takes a long time, maybe though intensity is low, but it contains lots of energy, and energy density is high. And finally, as I said in my review, the author uses some relation compared with experimental data, and in my opinion, this approximation, it doesn't correspond to experimental data in hydrodynamics. It doesn't correspond to the real situation. And in addition to that, the author uses experimental data which doesn't say anything about density. But this comment is connected. The plasma in the work described by the author is not good. I also have some comments when the second two-temperature analytical model plasma is not described. Look at some slides, some figures. 30, 31, you may see colder electrons so badly. In reality, these are not cold electrons in ordinary plasma. They're talking about electrons with energy sufficient to generate alpha radiation. So I think there's some confusion here. The level of cold and hot electrons. Electrons usually considered hot because cold electrons is energy less than 1 kara. But you get the feeling that in the end, in the second half of the work, hot electrons in the text of the thesis. And another important comment, which I included in my review, calculation of cross-section of the coating generates radiation. Maximum energy for aluminum, maximum energy of electrons is 20-30 kara. And how accurate is that? There's formulas. But, and for final comment, I didn't like so much the text. Many misprints, inaccuracies. But this, I think, is generally true. But in general, the candidate's thesis, I think the amount of work and results obtained by the applicant allow me to say that the thesis corresponds to the requirements of St. Petersburg University and level, not only of the university, and the applicant deserves to be awarded the degree of candidate of physics and mathematics. Thank you, Andrei Borisovich. Maybe we change the procedure, and so maybe Maksim Vladimirovich will answer questions of Andrei Borisovich. So let's give the floor to Maksim Vladimirovich now. Thank you. Let me start with the very beginning, with the first comment. First of all, I included reverse break absorption. I agree that in my thesis, the strange paragraph and more energy about 1 keV. So frequency electron ion collision is reduced to few nanosecond. I agree with the observation regarding the collision frequency, and to assess the effect of temperature on the inverse break-in absorption. This would be more appropriate to compare inverse collision frequency. Estimate of several impacts of 1 nanosecond for electrons will be much higher. So this paragraph should be rewritten as follows: with goes down. So this can be explained. As Formula 9 shown earlier, absorption coefficient can be optimized. Let me show this slide. Can you give us slide number? We cannot. Unfortunately, I did not include this formula, and in this calculation, it's necessary to optimize divided by lambda, and in this in single dimension is division or laser spot bigger. So that is why in my work not with the small density gradient. And this is well, 1 keV. But if we take, for example, lambda 1 keV, the temperature will be 3, and absorption coefficient calculated by the formula approximately 1%. As it can be seen in this case, the mechanism of back absorption is ineffective. But when I pre-impulse, I take this into account. As for the parametric absorption mechanism, I usually it's considered these two processes play a significant role in when the model is bigger than lambda. That's why I didn't include with plasma, with local plasma, the small density coefficient. And after your comment, I studied, and I know there are many articles been published which show a significant role of lambda. Yet our algorithm of hybrid modeling, I agree that this should be included in my thesis. As for pre-plasma, in general, I agree that density certainly should be modeled three-dimensional, but usually single modeling, if laser spot is much bigger with uneven plasma, in that case we get some average distribution, density distribution. It's obvious that as laser radiation goes down less than 30 degrees, so the error will be more than 30. The level more than level approximation is 30 degrees. Is not good. At 60 degrees, it cannot be applied. And I'd also like to say that in my task was to create a quick working algorithm. That's why there's single calculation, peak calculation. But yes, in the future, I will use 2D modeling, hydrodynamics I'm going to use. And now, as for hydrodynamic, I did not take the role of nanosecond duration, so it should be described. In this slide, it shows that I took into consideration spontaneous emission, duration 1 nanosecond, which she also described in my thesis. And as for approximation, does describe in general, yes, a plasma profile doesn't describe well, but usually it's necessary. No density gradient up to and in this range, approximation is quite well. It works quite well. Also, I'd like to say that in my modeling, density profile has been transferred is only for test. Is only for test purposes. As for methods produce gradient or pre-plasma concentration of single dimension calculation, it works quite well in quite a wide range, and it's critical. Produces the result. So the Helios shown in figure 18 is comment 4. About confusion between cold and hot electrons. In my analytical model, we used three distribution: lower starting plasma temperature. Usually, there's two other temperatures are connected with interaction between the target and the main impulse, and the electrons with these two temperatures usually called cold and hot electrons. Cold electrons have kinetic energy between dozens. Hot electrons have energy between several hundreds keV. And in the model itself, the temperatures, the lowest temperature, not been described because the energy is too small to be used. They serve only as reservoirs for hot and cold electrons. So that's why the number is not equal to total number of electrons in the target. I would like to say that in this case, between cold and there's no clear border between cold and hot electrons. Hot electrons will have energy. So cold electrons, several dozens keV. And if you look at laser emission, so cold electrons will have energy of hundreds of keV. Or cold electrons have energy of 10 keV. So this terminology made the description easier and can't be accelerated because of counterflow. Now it's a question about cross-section. In the original the formula is derived as approximation of experimental measurements for ionization cross-section for U less 20. And in other work, experimental cross-section, but 100 shows if they correspond quite well. So I tested applicability of this formula. Maksim Vladimirovich, I understand. Unfortunately, our colleagues can. If you want to sense, if you want, I hoped that you. So this is the last slide. Unfortunately, this slide is not in my presentation. I gathered big base and database compared how they correspond with cross-section ionization, and as it can be seen, it corresponds quite well for a wide range of chemical elements and a wide range of intensity. Mega electron volt, it also is quite well described. So I think this formula can be used. So that's, I think these are the five main, these were the five main comments. Thank you, Maksim Vladimirovich. Andrei Borisovich, are you satisfied more or less? Thank you. Now I would like to give the floor to Sergeyev Vladimir Yurievich. Please, your review. I would like to say something what I liked, and indeed the significance of this subject is growing, but the third generation are quite expensive, and so developing analytical study of such laser sources is quite relevant today. Should be noted that the author has dealt with many complex processes and with the peculiarities of modeling was able, as you can see, is a long literature list, and besides Maksim Vladimирович's study, conducted a number of experiments. The experimental part is quite impressive. Description of these processes are ultra-short sources. So this make good impression. Now let me proceed to critical comments. On page 76, figure 27 is a comparison of the absorption coefficient, calculate approximate analytical solution, and direct numerical calculation is on the small parameter. However, parameter changes in the range from 0.01 to 10, with a good agreement between the numerical calculation and the analytical solution. So I would like to comment this. In figure 48, page 119, you can see half width of the line. The half height is greater in the case of target with a structured surface than in the case of target with smooth surface. So according to the Holzmark theory equation, the width of line is proportional to density. Then we can expect that the electronic density of plasma, the structured surface, should be greater than in the case of plasma with smooth, so target with smooth surface. Then next, in table 4, page 118, 1 cubic centimeter is 2 times smaller for a target with smooth surface. So I'd like to hear what the author thinks. High electron density described like 10-23rd degree require self-absorption, or maybe the absence, which can be important, or excited states, agitated states. So I'd like the author also to comment that. And the author contains no small number of misprints, inconsistencies, and I have some examples in my review. I will not give them here, but these comments do not affect the overall positive impression made by the thesis, and this is a complete scientific work. That is why the thesis corresponds to the main requirements. established by the order on the awarding academic degrees in Petersburg University, and the applicant deserves to be awarded the degree of candidate of physics and mathematics, specialty 010421, laser physics. Thank you, Vladimir Yuryevich, Maksim Vladimirovich. As for comment 1, absorption coefficient, Helmholtz equation. Of course, the model was created and is a misprint. And was calculated using the above-mentioned analytical model and reverse break absorption on approximate model. That is why it corresponds from 01 to 10. As for the second drawing figure 48, which unfortunately you cannot see in this slide. Thank you for the comment, and indeed I checked the figure for flat targets as 10 microns is approximate spectrum. For some reason I gave one specific measurement, and so I have changed this. So the figure 48 now looks like this. So the eighth line is slightly different, so it's not bigger. It's the width is for all three targets is approximately the same. As for definition of plasma temperature is a challenging task. It's common to not to pay attention, because in my experiment there are many factors which not taken into account. In the figure 4, the plasma temperature was measured, is obtained from experimental measurements, and here I show a comparison of spectrum with 500 electron volts, plasma thickness from 2 in the 1023rd to 23rd. So the lines become much wider, and that's why density 2 times 10 to the 23rd degree. So in this degree, the relation and the subtle structure corresponds to medium spectrum, and maybe it will be better to use different density 4 by 10 to the 23rd degree. At this density, we observe good coincidence between calculations and the same line width we get. Yet this mistake does not affect main scientific results of my thesis. As for self-absorption, my model was built on an assumption of maximum simplicity and clarity, and in this case the lack of self-absorption limits the area of model applicability to the calculation of optically thin layers only, and approximate thickness considered my work of near-surface laser plasma, but micron self-absorption is negligible. And in the future, I plan to expand the model's application to a thicker plasma layer, and in this case, self-absorption will definitely be taken into account. Well, that's it. Thank you. Vladimir Yuryevich, are you satisfied? Yes, in general, I'm satisfied. But comment 4 is contains, but in the first answering the first two comments, Maxim Vladimirovich himself said that he forgot something or he made a mistake. So I think that should be more careful. Yes, of course, I will be more careful. Thank you, Vladimir Yurievich. Next, we shall give the floor to Bychenko Valery Yurievich. I will be very... So what I wanted to pay attention to for laser can provide highest and since the work is highly relevant. Different. It can be used in different spheres. And as for the thesis is dedicated to modeling such radiation, obviously there's laser plasma interaction. That is why I think it would be logical if the thesis touched upon process of interaction of radiation with matter. It's also important. And as always, and it's also interesting to know what is the purpose of this, because it will be interesting to understand on simple examples the models, X-ray radiation described here. If you have any ideas, density, temperature distribution, these models can be used and are useful. Can be used by. So, or this could be converted if the model already exists. Width of lines, which sometimes is very necessary. As for the theoretical findings, I think this model is interesting because it's well known, as we know well. Does not release it. And this, of course, should be taken into account. So the applicant has taken a step in this direction, but at least he's taken this effect into account. And unfortunately, cannot be on the other hand, it's Monte Carlo model, but the combining results of these two, you get good valuation. I have some comments also. Was very useful to take into account cell agreement field, Monte Carlo method. It is this with the help, introduced critical energy. And maybe this is good, but would benefit if the author was able to compare the correspondence. It could be seen that empirical approach and my second comment is more of a wish. The last slide, which described X-ray sources, generations, these, as a rule, the more brightness is more interesting. Average brightness by time is not necessary to obtain exceptional brightness. And so the brightness issue, traditional source, was competitive, already known. That is why I will finish my speech by saying I think that the applicant proved his qualification is a unique study which corresponds to the main requirements on the sets of the order on awarding scientific degrees at St. Petersburg University, and the Sedov Maksim Vladimirovich deserves to be awarded the degree of candidate of physics and mathematics. Thank you, Valery Yuryevich. Maksim Vladimirovich, please answer in comments. The loss of energy is taken into account, obtained in empirical formula. Unfortunately, nobody can see your slides. Just say what you wanted to say. Would be good to show a formula here. On the basis of this formula, it's tested in obtained by Horny and Klimo in 2015. The single dimension peak calculation. The temperature 3E. It changed, and then they recorded this peak code as electron energy when they passed through foil, and they recorded a loss of energy, ion energy, acceleration, and it shows that this approximational formula, which I used, corresponds quite well. And I'd like to also the slide which shows Monte Carlo dependence. The peak code shows they correspond quite well, which means this half empirical formula, because reflection is taken into account correctly. As for the second comment, but brightness, let's compare now, make the comparison now. A stick laser is by Max Born experimental setup, 1 kilohertz laser focused on a spot with a radius of 8 nanomicrons. Intensity is 10 square centimeters, because the normal drop radiation. The conversion coefficient in this case is 8 by 10 in -5th degree, respectively 2 to 2p sterdian. The average brightness in this case is 4 by 10 in the 8th degree, one divided by from comparison. The comparison, X-ray tube brightness is 10 in the 8th degree, so the brightness of such laser source is 4 times higher than the average X-ray source. Valery Yurievich, are you satisfied with the answers? Repetition frequency kilohertz. Okay, sorry, I missed that. Thank you. Now I see. So in general, yes, I'm satisfied. Thank you. Evgeny Alexandrovich, I'll try to make it quick because my colleagues have spoken already with their comments. I'd like to start that indeed the width is been measured by several mechanisms. This is a quite complicated calculation, as was Holzmark regime, more accurate plasma spectroscopy. This Lyman knife has not been implemented because its intensity is focused the central component and at relatively low so-called pulse mode at high density, but doesn't go to static mode. It goes into a modulation, a rotation effect of agitated charged particles. But this is, in conclusion of this, I'd like to say that it's impossible to cover everything. So this is a very minor point in the thesis, and in a nutshell, it's very complicated to calculate. Another point is that, as was mentioned already, the physics of interaction of relativist laser radiation is very rich in different phenomena, such as parameter instability, which occurs in a number of recent experiments conducted by Anatoly Fainov group, who's now deceased, laser installation volcano in UK, and interpretation of which I took an active part, so that on the surface of relative density, parametric detectability, which results in fluctuations. So physics is complicated and interesting. And in conclusion, would like to say that it's impossible to cover everything. The thesis, and taking into account such subtle effects, and looked at more important effects. So one complex algorithm, one complex program, which the applicant, in my opinion, has managed to achieve. The relevance has already been discussed here, and it's important that the algorithm can be used, installed at a PC workstation, and as in addition to what has already been mentioned, was partly calibrated compared to experiments, so that in my written conclusion I mentioned that in the English text there are some inaccuracies, so like missing articles or prepositions, but this has nothing to do with physics. So I believe that in general the thesis is on a high level, has been performed on a high level, and corresponds not only to Russian, but I'd like to say American standards as well. I know both, I'm very familiar with both, and the applicant deserves to be awarded the degree. Thank you, Evgeny Alexandrovich. Maksim Vladimirovich, will you please comment, if you have any comments? Okay, so I will learn English better. Yeah, the article issue with articles for non-native speakers of English is very common. Well, Igor Chislavovich, Mashek, following the tendency, I will make my feedback even shorter. I have a positive opinion of the thesis. It certainly has novelty. It's certainly relevant. Which already discussed here, and novelty, of course, is in the compromise method of a hybrid approach described in the thesis. It's not only experiments; it's about numerical modeling, which can be used in the. So what is the art of possibility, which Maksim demonstrated in his thesis? It's a good impression. Experimental part makes a very good impression. I know what it costs because organization of the part in St. Petersburg, I actually took part, and I saw how Maksim works. So it's quite reliable and correct. So I will not give any critical comments. I only have one comment about the way I only have one critical comment about the presentation, but okay, let's wait for the future, for the improvements in the future. I think the thesis corresponds to the requirements set by the order, St. Petersburg University, the order of awarding academic degrees at St. Petersburg University, and the applicant deserves to be awarded degree of candidate of physics and mathematics, specialty 010421, laser physics. Paragraph 11 of the above-mentioned order has not been violated, and I think that Maksim Vladimirovich deserves to be awarded the degree of candidate of physics and mathematics, in laser physics. Thank you, Igor Chislavovich. Maksim Vladimirovich, no need to answer. Thank you. I will take your comments into account. Now it's my turn. It's very easy for me to talk. I have to talk about novelty. A lot was said about it. No need to talk about results. What I would like to say, mention something that I liked, and the main conclusion. As for advantages, I would say the use of modern experimental equipment, which me personally, I'm happy to say, is in the research centers of scientific university in St. Petersburg University. So it's good that we can obtain results, demonstrate good theoretical work. And now my comments, because I have been working on a council for 25 years. My critical comments are maybe a little bit formal. My first comment is, in my long career, I have never seen a single thesis free from grammatical and spelling mistakes. And unfortunately, Maksim Vladimirovich also has such mistakes, maybe a little bit more than or the average, for example, or there are some spelling mistakes, inaccurate captions, and which irritates the reader a little. Secondly, equations 81, 85 introduced constant C1, C2, C3 close to 1. So usually they are around 1. So, but then on page 102, the values of these constants are C1 250, C2 0.25, C3 0.3. This creates two questions. Are these the same constants, or how the value of these constants affect how variations of these constants affect the final result? And my third comment, which has indirectly already been mentioned here by Vladimir Yuryevich and Igor Chislavovich, also mentioned this. As can be understood from the text of the experimental studies, optimization of laser plasma have been conducted. Neither in conclusion nor in the beginning of the work, where novelty and provisions to be submitted for defense are presented, the experimental obtained data have not been discussed. From my point of view, this is a big omission, and of the academic supervisor as well, because these are good conclusions, good results. So it's a shame to not to give them. These comments do not affect the merits of the thesis and the results. This is a good experimental work, theoretical and experimental work, and in my opinion, I will not read this whole formal paragraph with all the dates and numbers. In my opinion, Maksim Vladimirovich certainly deserves to be awarded the degree of candidate of physics and mathematics in laser physics. And that the finish. May I answer your comments, please? Yeah, I've been too quick. As for misprints, I apologize. I edited the text, and unfortunately I cannot make it. But as about the equation, yes, these are the same constants, and it's 150, not 250. And here I agree that the all order of 0.1 to 100, and if the constant is 1000, because it's not big, so that's a relative question issue. And as for experimental results not shown, and indeed the experimental results, some peculiarities, the influence of the target surface, but my thesis is mostly theoretical, so I decided not to include experimental results. So that's it. This is my answer. Thank you. Does anyone present here? Would anyone present here would like to speak? I'd like to say a couple of words about the constants. It reminds me a joke. Let's assume pi equals 5, otherwise we won't get the result that we want. So the constants, this approximation is really funny. Thank you, Evgeny Alexandrovich. Alexander Alexeyevich, let's give the floor to academic supervisor. So we've gone a long way together with Maksim Vladimirovich, and I'd like to say that, of course, the results are positive, as you can guess, and I'm satisfied. Of course, in the beginning of our work, well, we had a period of big uncertainty if I should run experiments or do something else which distracted the applicant from the main task. But this oscillation range gradually grew smaller, and in the end, especially after he graduated his PhD course, he worked in IT sphere, and so this numerical modeling attracted him and enabled him to create this hybrid code, which we started with Irja and Andrei Klim, but then it was maybe too early and we never completed this work, and Maksim Vladimirovich managed to put it into a real, compact, comfortable code which you can use on your workstation and obtain desired results. This is a good result and a good work. That is why I I am for awarding the degree. Thank you. Thank you, Alexander Alexeyevich. Now, I have to ask everyone who does not belong, who's not a member of the Dissertation Council, to leave the room. Thank you. Thank you. Now we shall have the open individual voting and on awarding or not awarding the degree to Maksim Vladimirovich, candidate's degree of candidate of physical and mathematical sciences or not. But before we, I would like to summarize the results of our discussion. In generally speaking, the work is good. Our summary is the work is good. And the applicant deserves the degree, but we've got many critical comments. And so hopefully, Maksim Vladimirovich, so please consider your shortcomings, weak points. The individual voting. Andrei Borisovich, your opinion? Are you for? Yes, I'm for awarding the degree. Vladimir Yurievich? I'm for awarding the degree. Valery Yurievich? I'm for. Evgeny Alexandrovich? I'm for awarding the degree. Igor Cheslavovich? I'm for awarding the degree. And me also for. Unanimously 6 votes for, no other opinions. So, Maksim Vladimirovich, we award degree to you, and now I can congratulate you already. Now I would like Maksim Vladimirovich to give his final word. So, following the tradition, I'd like to thank members of the Dissertation Council, and it was so easy when I is quite difficult to put together a Dissertation Council. So thank you, dear Council members. Thank you, my academic supervisor. We've worked together for a long time. Thank you for the good discussions. Thank you for Mr. Andreev, who came to support me. So basically, that's all I have to say. Thank you, thank you. The session is over. In conclusion, I'd like to thank our colleagues. Unfortunately, we can only see their faces. Hopefully, when you become members of our Dissertation Council in the future, please come and visit us in St. Petersburg. It's a wonderful city. Thank you, everybody. Thank you and goodbye. Thank you.